You may please, okay, fine, thank you. Please put your attendance. Fine, thank you for your attendance. Now we'll be talking about, or maybe we'll just recap what are the components we have already discussed in our last class regarding bioequivalence studies. What are the important factors we considered, and those things I have already talked in a PPT. I will also highlight the textbook portion because I'm always suggesting please go through the textbook so that you will have a concise, and I will say in a concatenated manner, the things should be falling in place. So that's why I always try to put you context of the book also. I think my screen is already shared. This is Remington Pharmaceutics book, right? As I talked about this chapter. So bioavailability and bioequivalence, we already discussed it. How the bioavailability can change. What are the things we are measuring? I think my screen is visible. We are measuring area under the curve. We are also measuring the peak height concentration. We are also measuring the time for peak concentration. These three things, normally people, when you are going to do bioequivalent study, is going to be considered. It is going to be important. We talked about dissolution things, we already talked, so I'm not repeating what are the important factors which can actually control dissolution. Absorption factor, what are the important things? How much it is going to be soluble, how much time it is staying there, what is its hydrophilicity, hydrophobicity, all those important parameters is also going to talk on this thing. Properties of the drug, so what is the dosage form we are using, rate of absorption. So we also learned about minimum effective concentration, minimum toxic level, drug profile. Those things I have already covered up. This is the case I was trying to say in our last class also. I'm having three formulations, you see, their profiles are all different. I'll just try to focus here. Drug A, B, and C, three different formulations, for example, I'm going to give. And you see, A, B, and C are totally different. Even if the total area is possibly not definitely same here, I can see the B is very small height, which is always below effective level. A and C looks very similar, but still A is better because A is not reaching the toxic level. C is not good because it is already crossing toxic level and falling it down rapidly. So essentially, we cannot have any effect from these kinds of drug concentration. It is very important to know that. We have already studied these aspects. I will not discuss on them. So we should have a basis how we are going to do a drug comparison. Bioequivalence should be compared. Alternatively, we can find out the pharmacological action, what you are looking for. So concentration or drug actions results must be there. And then we talked about evaluation of bioequivalence data, how I'm going to do single. I think you remember, we can give single dose. We can have, we can say, we can have two groups and we can make some cross validation. So one group is going to get one drug, then B. For example, I'm having A and B. So those situations I have already discussed in our last class. If you please go through the presentation or the recordings, you might be knowing about. Now, these things we already covered, different drug, how much time it is going to take, what is the area, how should we compare, and 90% confidence level portion also you talked. Okay, so these are the simple profile. One thing I need to tell you, one need not be limited by drug blood level profile. That thing I'll just speak for 2-3 more minutes in this class. Okay, I think my screen is visible, right? Is it visible? Can you respond?
Yes, sir.
Okay, thank you for responding. So most of the time, I was telling that, okay, we are taking one drug, maybe tablets, capsule, or injection, and we are measuring the blood concentration, I mean to blood serum level, and we are seeing how it is going to change. So this is time, and this portion is essentially concentration in blood or serum. Okay, that is fine. We are, okay, that is one portion, but one portion we are ignoring is that how much the drug is coming out through your urine. That is also important, right? Urine you are not measuring every second, right? Maybe every 2 hours you are going, or 3 hours you are going for urination, and we are measuring the concentration. So if I want to look for the urine profile, how urine concentration, of course you will not get all the points, 1 point, then another point, or maybe, for example, this is the concentration in urine, your drug, we are measuring. It is not that it is only in your blood, right? It will be some drug will be metabolized. So for example, urine concentration and time. Most of the time we are talking about the blood concentration. We are completely ignoring the idea that some portion is also going into your urine, which is not going to be considered. You are actually ignoring it. Now, how the blood concentration, so actually how the blood concentration is happening? Thing is that you try to understand, we are having a drug which is being absorbed. So this is absorption process. It is coming into the blood pool. It is having, for example, we are talking about your kidney. So this portion is, for example, excretion in urine, and it is going out. So essentially, if I say blood concentration profile, if I say concentration as DC in blood with time, it is not only simply how much rate of absorption is happening. So I can say this is actually rate of absorption minus rate of elimination. So essentially from this profile, if there is no elimination is happening, if you are not going to measure, what will happen? So essentially, if there is no elimination profile, we are expecting the blood concentration will go like this and it will stay lifelong. It does not happen, right? It goes up and falls. So essentially, these absorption and elimination, both the things are happening here. So essentially, it also represents a concentration in which is there in your body, which is actually coming out of this body. So essentially, even if you are measuring only the blood concentration, you just try to understand one thing. If I only know the blood concentration, do you think that I can measure the amount of drug, total amount of drug which came actually through this? So if I know entire concentration of blood also with time, I cannot tell you how much was absorbed, because there is always some loss part, right? This curve is also happening. So essentially, if I simply say absorption curve may be like this. Sorry, I'll maybe I can give some other color. And why this thing is important also I need to tell. So for example, this is only absorption. and I'm assuming that there is no loss in urine. And of course, if I consider the loss due to urination, because some drug is constantly being lost through urine. So this is input and this is output, loss. So what will happen? Initially, there will be no loss anyway. It will be very small. Some changes will be there. So essentially, this graph is coming from this one, this height, which is coming into blood, minus, for example, this height. Some cases, it is not true. So I will have very small concentration, even negligible. In this case, negative only. So we are actually measuring the blood, but ideally, we should also measure the concentration lost in urine. Why? Because the drug was sometime in this blood also for this time period. So if I say the blood concentration data and how much you lost through urine, if I sum them together, so the profile, for example, I'm saying blood profile plus urine profile, if I sum them together, this thing is representing about the amount absorbed. Or if you are getting it or not, you just tell me. So this is coming in and this is going out. So for example, every month you are getting some 3,000 rupees or 4,000 rupees, and there is always some expenditure. So if I simply see your account balance, can I always, I mean to say only the how much is available. If I see, does it reflect how much you had your income? No, there is a continuous input is there and continuous expenditure is also there. So if I see your available balance plus how much expenditure you made, if I sum them together, all the profile, I am likely to get what is your income, how much input is happening. So bioequivalent study, even if we are ignoring for most of the drug, we are only measuring the blood level, it is always advisable, you can always have a look on the urinary excretion, if the urinary excretion is significantly higher. So we need to also know. So that's why it is telling drug concentration is determined in the urine, some time interval, and we are multiplying with the volume of urine. So I can actually add up both those things to know or to modify this concentration profile as we are saying. Now, those things, bioequivalence things we already discussed, 90% confidence level, all those things, we are taking around 20 to 30 individual. For each of them, I am measuring blood concentration or urine concentration also. And then I'm taking an average. And if this average is going to be very similar with my standard drug, which is already there in the background, we are normally doing bioequivalence, means we are comparing with some other one, right? There is always two things. One is reference with which you are comparing, another is standard. I mean to say, sorry, test. So reference profile is already known. That drug is already old drug, people have already analyzed. And the test drug you are giving to some healthy individual, some 20 to 30 individual. They are taking an average of this drug profile concentration, and this reporting is normally done. And that should be always within 90% of the confidence level. Three things should be considered. In our last class, we already talked, just because we are going further, I should just make it confirm you understand. So one thing is the area calculation you will do. And for all the 30 people, so roll number 1, roll number 2, roll number 3, roll number 4, everyone I'm injecting and I'm measuring the area. So for example, I'm getting the area 5.36. Somewhere I'm getting 6.39 or 6, 5.87, like that. I'm getting some variation will be there. Everyone's graph will not be same. Someone will have like this, someone will have like this, someone will have very close to that. So individual case, I will measure the area for individually. And once I make the individual, I can calculate what is the average and plus minus standard deviation also. You know how to calculate standard deviation, right? If you don't know, you use Excel and you will learn. So average and standard deviation I'm getting. So for example, this is the average value and I'm taking the deviation also. This is the highest, this is the lowest. So this is for your test drug, as I was telling in our last class also. This is example for your test. For your standard drug that is already available, which is already studied, people have already done, So I'm also getting, for example, this is for standard. So what I'll say, okay, my test drug is fitting within the standard range. You see, if I put a line, so I can see my entire drug, test drug, is fitting within this. Sorry, this is your reference drug, is already fitting with the test one. So they are not significantly different in 90% level. So they are similar. The distribution is similar. So I can say bioequivalent in terms of area. Of course, you have to do it for maximum concentration also. Same process you will do. And time for maximum concentration. So all the three things you have to average. Here I found out the area versus comparison is okay. Cmax comparison you have to do, okay. Time comparison you have to make. Once the all three okay you are saying, then I will say the drug, your test drug and reference drug are bioequivalent. Am I clear? So this way normally test is done. This is one case study I am just talking about. Same thing is already done with all other formulations. So that will actually, I'll conclude this bioequivalent study, how we are going to do, how people, everything we are not going to cover. This is, for example, one drug, this is another drug we are comparing. You see, they are different. Of course, the profile is not very similar, not exactly similar, but you see time for maximum concentration is nearly matching, not much different. Height is also nearly equivalent and area is also same. And we always told you, I need to tell you that always there is a 20% gap is always permitted in pharmacological study. If there is anything varying by 20% here from one another, that is always acceptable. So we should take the reference plus minus 20% and your data should fit into that. So this idea we already have discussed and I'll just conclude it here. Now, once we have done this, probably I should go into, one second, I should go and go for here. That is your chapter 7, which is primarily talking about pharmacokinetics and pharmacodynamics. Of course, we have some other study material as well, but just for your understanding, what are the things we are going to discuss in this class? We are going to discuss about how we are going to measure analytical consideration, how the measurement will take place, drug concentration profile, pharmacokinetic model, will speak on that, rate and order of reactions, okay, and instantaneous input with instantaneous distribution models. So basically, anyway, we'll go into them in coming days possibly. And just what is my intention of this discussion is basically to have a pharmacokinetics model and understanding the pharmacodynamics. These two things I need to consider. You please go through this chapter, so that's why I am showing you and I will be discussing now. Okay, so this chapter is, I mean to say, now chapter 37 we will be mostly focusing on this. Now coming into difference between pharmacokinetics and pharmacodynamics. These two things are really very similar. Many people are actually confused how are going to distinguish, how are they important. Those aspects we will be considering. I have some other study material. Please go through the brochure here, I mean to say the folder. So when I'm talking about pharmacokinetics, we are essentially talking about the drug alone, drug concentration. We are looking the drug concentration throughout our system. Okay, only concentration. And sometime we'll be talking about pharmacodynamic. That is actually response. What effect you see? For example, you are taking one medicine, for example, for you have some muscle pain, and for example, you are taking some diclofenac. Okay, so it is actually a skeletal muscle relaxant. So you will have, you should feel that okay, the pain is subsiding or not. How much dose you are taking and how much result you are observing. So basically, dynamics talks about dose and response. They don't consider about concentration. They only how much I am taking, how much is the result. Result is more important in this case. When I'm talking about kinetics, why I need to know about kinetics? This is the first question comes to anyone's mind. What is the purpose of learning kinetics? So basically, when I'm talking about kinetics, you need to know that is always with time. Now, okay, if it is time, I'm not sure. In your batch, you have not studied the chemical reaction engineering part. So any compound, if it is going to be degraded, it is going to be converted, any compound. For example, this is one vessel. Our body is also like a vessel, right? There are many vessels we are considering. That is compartmental models. Our body, we are assuming different compartment. I may assume that my entire body is a single compartment. Okay, whole thing is just one. That is our single compartment model. Why we need to consider? This is only imaginary. As of that, nothing is there. For our understanding, for our calculation, we normally assume the entire body is same. What does it mean? If I'm taking some drug, it is going everywhere. It is going equivalent way, and that's all. Just one compartment aspects we are considering when I'm talking about single compartment model. Many people do multiple compartment. What are the multiple compartments normally people consider? The first compartment they normally consider is the blood is a separate compartment, and few specified organs, very important organ for our pharmaceutics perspective are liver, kidney, and sometimes we also consider about brain. So basically, how you are considering, if I'm considering blood only one compartment and liver and kidney another compartment, we may consider if it is going to affect or if it is going to be a drug which is going to affect on central nervous system, CNS drug, we are also assuming the drug concentration in the brain is also, CSF is also important. So that means drug is actually going into brain. So blood, brain, barrier, all those concepts will come into picture. So anyway, now I'll just assume that there is only one compartment. That means my whole body is a single thing. If my whole body is a single component and I'm injecting or I'm taking some drug, so this is the input. For example, I'm taking single dose. So what is happening? As I was telling, there is a rate of absorption and rate of elimination. Somehow it will be eliminated throughout the entire system. I'm not considering a separate unit. So anytime the drug concentration, how much it is going to change. So there are many mechanistic view. Some people say that the drug concentration change depends on, it is proportional with concentration. What does it mean? If more drug is there, the rate of loss will be also more. Very simple logic. Most of the time, people assume the change of drug concentration in your body compartment, it is proportional with how much is there. It's like you have more money, that means you will spend more. If you have less money, you will spend less. So same kind. If I'm having more drug in the tissue and fluid, the rate of change, the rate of loss or concentration drop, that rate depends on concentration itself. And essentially, these kinds of model, if you know about basic reaction kinetics in chemical engineering, I'm not sure, you have not studied, I believe, that rate is known as first order. Most of the time, drug elimination in our body, when we are assuming, we consider the rate as first order rate. So that means dc dt will say equal to minus k into c, some constant. And you know, by this time we can do some integration also, like mathematics statement. I will integrate it c0 to c, 0 to time t. So what will happen? I will get ln c by c0 equal to minus kt, or c equal to c0 into e to the power minus kt. That is the first order decay rate of concentration. Now, what does it mean? First order means at the very beginning, very high rate. As the concentration falls, rate also falls, and going on. And it will continue to infinity time. It will never be zero. First order rate will never become zero. It will very small rate, it will continue. So you see, if we are seeing that blood concentration or drug concentration in your body or tissue fluid is falling like that, we can assume that some first order rate is assumed. But in this kind of behavior, if it is a first order decay, I'll always see the concentration is slowly dropping. Okay, if there is any decay. And most of the time it happens like that. Its decay happens like this first order only. And when it is absorption is happening, absorption rate is, for example, again, absorption also depends on how much drug is there in your. So basically, if I'll just put some 2 slides. I hope you understand the compartment part. This is one compartment things. Now I'm coming into another part. If I talk about a 2 compartment model, let me say, have I told you why this loss is happening? Why it is the loss? So this loss can be of 2 reasons. The first is that it is coming through urine. That's why urinary loss. Otherwise, concentration will remain constant, right? If there is no loss, then it will remain constant. But anytime we have seen the drug is losing, so that means somehow it is going out. And this is actually the loss through urine. Okay, how much amount of drug is lost through urine? So that we can calculate by considering. So this is the concentration profile in blood, and this loss is due to urinary excretion. Now, second component I'm coming into is that we are having a blood here, blood volume I know. And for example, this we are talking about is not kidney, rather liver. We are assuming a compartment as liver, and this is blood. What can we say? Liver from blood, every time they have always connected, right? Blood is coming, going. Now, when we will learn about metabolism, then you will see many drugs are actually going to be metabolized in liver. So otherwise your drug will remain there for a long time, right? But it will not remain. So what will happen? The liver job is to convert. It is a converter. So there is many enzyme systems are involved in the liver, which will actually convert this drug molecule. Maybe we can convert it into glycosylation. So many drug molecule will be capped, so their activity will be lost. They are no more going to be used up. They are having enzymes to break it down, chopping down the drug. So basically, it is done by enzymes. So if enzyme level in your liver is low, if there is not so many enzymes to interact with your drug molecule, so this conversion of drug to drug conjugate, for example, why this drug conjugate is required? Many will ask why it is important. Importance. There is 2 reasons. First of all, if the liver is not going to make its a conjugation. Conjugation means, for example, D, it is attaching one group, for example, C. This group is hydrophilic group. Okay, water loving. What will happen? This water loving group will make it more soluble, and much of the drug can be excreted also through urine. This is one reason. But conjugation will also have another purpose. If I am making it molecule, so for example, this is a very small molecule, okay, molecular weight, for example, 10 kilodalton, and I am having a conjugating enzymes which will convert and which will add a large chain along with this drug. Why this conjugation is important? If the molecule become larger, it will not simply drain away, right? I'm making it bigger. So it will not directly go and kidney and it will not be lost. Okay, kidney is like a filtration, you can think about from this perspective. So if my molecule is very small, like simple sugar molecules, they will cross, or sodium chloride, they will cross, water molecule will cross. But if I'm having drug molecule, that is also very small, but I'm putting a very big tag with it. So this become a bigger molecule, and conjugation can also stop making this filtration. So urinary excretion can be controlled by those enzymes. So I'm having bloodstream coming into liver, which is being converted. Not only conjugation, sometimes they will break up also. So, okay, maybe for example, dehydrogenase enzymes are there. They can also break up the large molecules. So essentially, the liver is going to serve the chemical conversion of your compound. You are taking, for example, alcohol, they are going to form ketones here. Completely a chemical laboratory. So once this ketone is produced, that will finally come and going to be excreted possibly. So it all depends on how much time the drug molecule is staying, what is the rate of conversion. So I can say, when I am having now, I'm coming into mathematical perspective, I am having a drug which is coming into bloodstream. So this is rate of absorption. I want to measure the blood concentration, and I need to consider what is the rate of conversion. Okay, rate of conversion, loss rate. So anytime if I say the drug concentration profile, as I told you in just few slides back, it depends on rate of input, rate of conversion, rate of output. Rate of output means the original drug is going through your urine. Okay, original drug being converted, so that is also loss. And sometime the conversion may also make your drug concentration increase. So sometime conversion may actually either add or minus, either plus or minus. Sometimes the converted molecule is more useful than the drug itself. That is called prodrugs. So conversion is essential in some situations. So that means after liver it is breaking down, then only it will be useful. So in that case, I can assume that the conversion is the integral part. Conversion is not a loss, and the converted molecule in blood we are going to measure. So total concentration profile will depends on how much rate it is coming in, how much rate is going out. Most of the time, if you do not know how much rate of conversion, that is essentially going to be second order. Why? The rate of conversion also depends on, it is an enzymatic process, right? For example, substrate, some enzyme. If you have studied, and I'm not sure, have you studied this enzyme kinetics kind of things in your enzymology class? Have you studied those things? Enzyme effect? So substrate is binding with enzyme, and they form substrate enzyme complex, which is again going to break down and going to form some product plus getting back enzyme. So settling things are happening. If you have studied enzyme kinetics, you can speak on that. Of course, there is some reverse rate of conversion is also there. I mean to say, from the enzyme substrate complex, they can split it off, and whole process is actually going to be converted. If I'm going to learn about enzymatic rate, V equal to, if you know, Vmax, okay, and into your drug. This is actually enzyme kinetics. Even micro growth kinetics also behaves like this. So this is a enzymatic conversion if I assume that the amount of enzyme remain nearly constant. That is true. because most of the time the enzyme concentration is regulated in your body. So if I know the enzyme concentration, how much available in your body or systems, I can always find out what is the rate of this conversion. So you see now that, okay, I'm having some blood concentration. Now it will be more easy for you to discuss about kinetics behavior. Why I'm discussing these? Because I need to know what is the expected concentration in your blood. That is my only job, or our only job, when we are studying pharmacokinetics. So rate of absorption I will calculate. I need to know the equation. And rate of elimination or detoxification I know, and rate of elimination. So if I increase my model in a bigger scale, then I will say that blood concentration is going to be the rate of absorption. I need to know the equation for that. Rate of elimination means through urine. People normally use, this is a first order, so I'll say K into CB. And rate of conversion, for example here, so we can also write like that, okay, some constant Vmax into concentration, one constant into concentration. Rate of absorption is how much drug have you taken. Okay, if I have taken more amount of drug in this is a gastrointestinal tract, I think you understand. If there is more drug here dissolved, then more rate conversion, then more rate it will come into the blood, right? So this incoming rate is actually dependent on, so what is the rate will depends on how much it will continue. Any drug molecule from one portion it is going in. So what is the rate? Initially, rate will be very high. I mean to say, rate of transfer will be very high, and sorry, not like very high, and then it will fall. So because the rate of transfer, I will say rate of transfer depends on what is the concentration in this here in your GI tract. Do you remember I talked about that? And concentration in this local blood concentration is very small. Now GI drug concentration will depends on solubility, right? It depends on solubility. How much is dissolved in the gastrointestinal tract, it depends on solubility. So this part I can also write is a K into the solubility of the drug and concentration in blood. You see, everything I'm writing in terms of concentration, of course, K1, K2, and elimination. Then, okay, I got the complete picture of a rate dc dt. What is dc dt? Rate of change of concentration in blood. So we talked about rate of change. Now, if I just summarize the whole picture, what is the purpose of this? So if I summarize whatever we have learned, rate of input, I already know. So overall rate, I'll show you some expression later on. Concentration change profile with time, as I told you, incoming rate. So for example, I'm saying K1. K1 is the mass transfer rate across your lumen. So gastrointestinal tract and blood, that layer. And I told you it depends on how much concentration I am having the drug solubility. So dissolved drug concentration, solubility concentration, minus what is the blood concentration. I'm making simple. We will have more difficult equations later on. And rate of elimination through urine. So this is absorption. This is urine, that is K2 into some constant of CB. And the last one is liver conversion. Okay, so another Km, like that. So once I know all the CB, I can, this is equation, right? Differential equation. I can solve it. So if I solve it, so I will get concentration as a function of all, if you know that K1, K2, K3, Km, all those things, if I know those parameter values, I can find out the concentration profile with time. So some concentration versus some time. That means with this model, I can predict, you can predict what is the blood concentration of your drug is likely to be there. You can make a picture of this because you have already done a modeling. So pharmacokinetics models talks about what would be the expected concentration. Please listen. Pharmacokinetic model, the purpose is to tell you what is the expected concentration of a drug or maybe similar drug, it may be known or unknown drug, which is very similar to someone else with time. So that means once I have made this, I can make a time versus concentration profile. Without doing, I can also make. I'm not studying the blood actually. I'm making a model. So, and for example, this is the minimum concentration required, and this is the toxic concentration. So what can I say? That okay, up to this time period, your drug concentration is above the minimum limit. So I can expect this is the values, this is the concentration I will have in my blood all the time. So this is about talking everything on kinetics. These are all talking about kinetics. Next part in our discussion will be on dynamics. Dynamics is a different study. Now, every time, if I know what dynamics, you cannot really predict every time. So for example, I know the blood concentration. Okay, for example, I'm doing a dynamic study. So I know the blood concentration. And I'm asking you, have you recovered or what is the response? How much you are feeling good, recovery. So for example, at different time you are telling, okay, I have not recovered, recovering like that. So that means this is your recovery with time. Am I clear? Recovery means, for example, fever. You are taking a dose and you are saying that nothing is improving. Then after 2 hours, you are feeling improved. So percentage of recovery, for example, and you are happy after some time. So this is a response you are getting. But what is the dose? And this is the dose. You see, same time I am measuring the dose also. Dose means in the blood. So at any time I can find out what is the concentration in blood, yes or no. So for example, this is 1 hour, or maybe this is 2 hours, and this is 3 hours. So I can find out what is the blood concentration in 2 hours also, and 3 hours also. How can I do that? By measuring or by pharmacokinetics. So I will know what is the concentration in the blood at 1 hour, 2 hours, 3 hours. I also know what is the response in 1 hour, 2 hours, 3 hours. This is the response. 1 hour, 2 hours, 3 hours. Then what I will do? I'll remove the hour. I'll simply plot them. Concentration and response. Am I clear? So for example, I know this is the blood concentration from this graph. This value, and this 1 hour, this is the response, 10%. So then I'll plot concentration, whatever concentration this one, whatever response this one, corresponding. So time versus concentration, time versus response can be converted into concentration versus response graph. Okay, increasing concentration, I'm getting increasing response, then probably it will be flat, no issue. So time concentration data, response concentration data can be converted, and once we convert it, you will come to know that what is the concentration when 50% of the satisfaction is achieved or 50% response is achieved. So maybe this concentration, I can see 50% of my response is achieved. So this concentration is known as, for example, effective dose ED50. 50% response I am going to get from these kind of dose. So essentially, I can say what is the expected dose I can also calculate for a new pharmaceutical formulation. That will be the overview we are going to learn from pharmacodynamic studies and pharmacokinetic studies. Anyway, I will focus on the textbook, not today, so it is already over time. So basically, in our next class, I will talk about what is the concentration versus time profile we are making. What is the concentration we should always over. You see, there is a different people might have different values, so forget about that. And you see pain score, for example, patient 1, I'm taking some dose, okay? Initially I'm very low dose, no result, I'm very high dose, then pain is relieving, okay? So this can vary between the people. So I'm concentration versus response data also we can find out. That is really important. Concentration response curve we are going to do. Pharmacokinetics model, you see what is the purpose of this when I'm making a pharmacokinetics? Predicting the drug concentration in blood and plasma. I told you very beginning, prediction is the more important things. Otherwise, if you can you measure every one people what is the blood concentration every time? No, it is not possible. Everyone cannot have the blood monitoring every time. So I need to make a model which will tell you what is the expected concentration in the blood at any given time. Calculate the doses, how much dose is required, because I told you the rate of absorption, right? So if my dose is increased, the amount of absorbed will also increase. You have to go into the mathematical model part. So I can also predict how much dose is ideal for an individual to get. Elucidation of mechanism, disease induced alteration in the drug disposition. If there is any change, what is the mechanism, why the people is losing, why the drug is not going to take over in this body or system, I can measure it. What is the disease related things? Yes, if disease is involved, the metabolism of the drug will be altered, right? So we can also find out, is there anything mechanism of drug-drug interaction? If there is two drugs is interacting, what will happen? Your drug concentration profile will change. So it all depends on if there is two compound and they are also interacting in this process. And it is also being used to predict the drug concentration versus effect relationship, concentration versus result. As I told you just now, that is going to result in a pharmacodynamics model. Rate and order of reaction, I already, you see, this is the example we are going to talk. Drug in doses form, releasing, dissolution, crossing the barrier, it is coming into central compartment. Okay, central compartments, we are normally talking about the blood things. It is going free drug, it can bound with protein, it can have metabolism, you see, activation, deactivation, polarization. Excretion can happen in urinary part mainly. Sometime in pulmonary excretion is also there. Some drug can be reabsorbed, it will be distributed over other compartment body and maybe excreted. So this is the things, you see, we are talking about the drug concentration profile. It is the concentration data after oral dose. So I'm taking oral dose, what will happen? It will initially increase, then fall. And this fall behavior, we are talking about whether it is zero order or fast order. Okay, so this importance, this gives us importance. Okay, you see, for example, this is talking about the zero order. Okay, zero order means it does not depends on anything. It's constant rate, it will decrease. Okay, we can have also for fast order. This is, for example, fast order. So anyway, we'll discuss about those things from our textbook in later on. And today time is over, so I'll stop it here.